we are going to get into something called prime factorization. So before we get to prime factorization, we would like to know as to what a prime number is. So we know what natural numbers are: 1, 2, 3, 4, 5, all the way up to infinity. It'll keep on going. So a prime number is a natural number greater than 1 and divisible by 1 and only by itself. So if you take a prime number, it can be divided by 1, but then every number can be divided by 1. So every number is going to satisfy that condition. The rule for a prime number is that it can only be divided by itself. For instance, take the number 2. Clearly, 1 divides 2. And 2 divides 2. Now, if you pick any other natural number, say 5, that's not going to divide 2. 7 will not divide 2. 11 will not divide 2. So the only number that is going to divide 2 is 2 and the number 1. Other numbers would be 5. If you take the number 5, 1 divides 5, 3 doesn't, 4 doesn't, and it'll keep on going. Is 11 a prime number? Absolutely. 1 would divide 11. Nothing else is going to divide 11. So the only number that is going to divide 11 is 1. And of course, 11, that's a given. And same here, 5. Elderly wrote 2 divides 2. Also, 2 is the only even prime number. There is no other prime number that is even. 2 is the only one. Very unique. And 2 has a lot of nice properties in mathematics. A composite number is one that is divisible by 1, divisible by itself, divisible by another number. So let's take the number 6. Clearly, 1 divides 6. As I mentioned, 1 divides every number. 6 divides 6. We know that. 2 divides 6. 3 divides 6. So I have found 2 numbers, 2 and 3, that divides 6 in addition to 1 and itself, the number 6. This would mean 6 is a composite number. So is 14 a composite number? The answer is yes. 1 divides 14. 14 divides 14. 2 divides 14. 7 divides 14. So there are two numbers, 2 and 7, that divide 14 in addition to 1 and itself. So 7 is a composite number. So just by using the logic of a composite number, we can realize something called a prime factorization. Now, if you look at that 14, I took 14 and I found out that 2 and 7 divide 14. 2 and 3 divide 6. And if you observe closely, 2, 3, 7, they're all prime numbers. So a composite number is divisible by a prime number whenever possible. So using that logic, we have something called the fundamental theorem of arithmetic. Don't get spooked by the word theorem. What does fundamental theorem of arithmetic say? Any composite number can be represented by a product of prime numbers. These prime numbers are what we call factors. When we multiply a bunch of numbers together, for instance, 2 times 3 times 2 is 12. 2, 3 are factors of 12. So clearly you can see 2, I broke it down as 2 times 3 times 2. So 2 is prime, 3 is prime. So it's a product of primes. So prime factorization comes from the idea of, fundamental theorem of arithmetic. Let me take the number 36. Let me think of a prime first. Well, 3 divides 36. I can write 36 as 3 times 12. I can write 12 as 3 times 4. I could write 4 as 2 times 2. And that's the best I could do. And that's going to give me the answer. So if you pick out those numbers, 36 can be written as 3 times 3 times 2 times 2, which is also 3 squared times 2 squared. If you notice, every single number in that product on the right-hand side is a prime number. So the right-hand side is the prime factorization of 36. We want to find the prime factorization of 64. So I want to break down 64 in terms of a prime number and a composite number. So 64, the first prime that I can think of is 2. So 2 definitely divides 64. So 2 times 32 is 64. Once again, the prime number will be 2 and the composite number will be 16. 16 times 2, 32. I can split 16 as 2 times 8. You can see the branches on the left-hand side result in numbers that are even. Not even, I'm sorry, prime. We want to come up with prime numbers. And A, can write it as 2 times 4. 4, I can write it as 2 times 2. One might be tempted to put 1 in here, but do remember the number 1 is neither prime nor composite. But 1 is a factor of every number that you can think of. So the number 64 can be expressed as 2 times 2 times 2 times 2 times 2 times 2. I'm multiplying 2 to itself 6 times, so 2 raised 6. So that would be the prime factorization. Typically, if you're able to write powers in different numbers like we did previously, the second equation, 3 squared times 2 squared, is the simplified version of prime factorization. Let's take the number 81. First off, I've got to come up with a prime number that divides 81. 3 will divide 81. We know the sum of the digits results in a number that is divisible by not a 3, then we have a number that is divisible by 3. So 8 plus 1, 9, 3 divides 9. So 81 is divisible by 3. 3 times 27 is 81. 3 times 9 is 27. 3 times 3 is 9. So I could write, 81 as 3 times 3 times 3 times 3. Which is 3 raised 4. We want to know the prime factorization of 363. Oftentimes you might wonder, well, what prime number should I pick? This is why we went over the rules of divisibility. Clearly, 2 is not going to divide 363 because the last digit is neither 2, 4, 6, 8, or 0. If you sum all the digits, 6 plus 3 is 9, 9 plus 3 is 12. 12 is divisible by 3. So 363 is divisible by 3. So if you divide, you can use a calculator. You will find that you can split up 363 as 3 times 121. 121 is 11 times 11. And you know that 11 is a prime number, so you cannot go any further. So 363 can be expressed as 3 times 11 times 11, which would be 3 times 11 squared. So we have 663. If you sum the digits, you will find that you will get 15, which is divisible by 3. So 3 divides 663, which will give you 221. But this is a bit challenging because 221, if you use the rules that we know for divisibility, none of the rules would actually help you here. So, which would mean either 221 is prime or 221 is divisible by 2 primes. So since you see 1 at the end, a golden rule of thumb is I will start testing 11, 13, 17. Those are the numbers that I would go for. So if you picked 13, 13 times 17 is 221. How did I know? I recognized it by that 1 at the end. Typically, you sort of end up with a number that for which you cannot use the rules of divisibility. You can look at the number and say, well, is it just prime? Or could I break it down further to determine what the factors are, if there are any, for numbers such as 221. I look at the last digit. If it is 1, and if I know that there must be a prime number somewhere, I will test for 11, 13, and 17. That is a good place to start. So in this case, 663 is 3 times 13 times 17. That is the prime factorization. So we want to find the prime factorization of 1440. So mind you, we've got to start with the smallest prime number that would divide 1440. So 2 would. So if you divide 1440 by 2, you get 720. 2 will also divide 720. 360. You may ask me, well, how did he recognize that 2 is going to divide 1440? The 0 at the end. Anytime we have 2, 4, 6, 8, or 0, that number is divisible by 2. 2 would divide 360. I'll get 180. 2 would divide 180. I'll get 90. 2 will divide 90. I'll get 45. Now, the last digit turned out to be 45. So we know from the rules of divisibility that if the last digit is 5, the number is divisible by 5. So 5 is the prime that I'm looking for. So 45 divided by 5 is 9. And the only way to split 9 in terms of prime numbers is 3 times 3. So the prime factorization here for 1440 is 2 times 2 times 2 times 2 times 2 times 5 times 3 times 3. So 2 raised 5 times 3 squared times 5. So if we go with picking the smallest factor logic, 45, I can split it in terms of 3, because 3 divides 45. If you sum 5 and 4, you get 9. And 15. Now 5 is the last digit, so I can split that up and write it as 3 times 5. As you can see, the only thing that's changed is the order of the numbers in which we multiply. So 8,316, I'm going to aim for the smallest prime that would divide 8,316. And if I use the rules of divisibility, the last digit is 6. So this number is divisible by 2. So 2 that would give me 4,158. Last digit is 8. So this number is divisible by 2, which would give me 2,079. Now 2,079, the last digit is not 2, 4, 6, 8, or 0. So that number is not divisible by 2. So I'm going to check for 3. So if I add all the digits, it comes to 18. And we know 18 is divisible by 3. So 693 times 3 would be 2,079. The next step would be to go for 3, because the last digit is neither 2, 4, 6, 8, or 0. If you add the digits, I get 18. 18 is divisible by 3. So if I divide by 3, I would end up getting 231. Now, here is the challenge. If you add those numbers, it doesn't seem to help much. So we have to sort of work our way by testing numbers other than the usual numbers that we test for. Divisibility rules we have for 2, 3, 4, 5, 6, 8, 9, and 10. So one of them is missing, which is 7. So let's start with 7, because that is one of those numbers for which we don't have divisibility rules. So I'm going to divide by 7. If I divide by 7, the result is 33. The smallest prime number that would divide 33 would be 3, and then I would have 11. So 8316, I can write it as 2 times 2 times 3 times 3 times 7 times 3 times 11. 2 times 2, 2 squared. 3 times 3 times 3, 3 cubed, times 7 times 11.